Hi guys, this is Nicole discussing two practice problems for your final. So these two questions are both taken from past exams. Okay, so one type of question you may be asked on your final is given a recursive method, and a recursive call or a call to that recursive method, what is the expected output of that method call? And as we can see, the method given is indeed an example of recursion. It says explicitly in the class name, recursion problem 1, but even if we weren't told that we're given a recursive algorithm, if the class name was just a mystery method, even if we weren't told, would you have been able to identify this method rec test as recursive? Yes. So what two cases do you notice present in the body of our method rec test? So there's the base case, right? If n is less than or equal to 0, return. And there's the recursive cases, okay? Rec test of n minus 4 and rec test of n minus 2. So even if we weren't told that we're given a recursive method, we should have been able to identify the method as recursive. The key giveaway being within the body of the method calls to itself, okay, within its own method body. So what's the output for the following code snippet? The way to do this problem quickly is by jotting down the tree representation of the recursive call stack. Okay, so pause the video and take a moment to do that. Hi guys, welcome back. And let's trace the changes to the recursive call stack. And also, I'd just like to note that I abbreviated, rec test to R just to make this quicker to write for myself. And here is what will be a recursive call stack. And, printing 2, 6, printing n isn't, a recursive call, but I just have it here for our reference so we can keep track of when output is happening. So, okay, so where do we start? Do we start at rec tests or do we start at main? We always start at main, right? And what are we doing in main? We have a call to rec tests for n is equal to 6. Is 6 less than or equal to 0? No, base case is not satisfied, so we continue. So rec test of n minus 4. Okay, rec test of n minus 4, we call r of 2, right? So in our visual that you might have also jotted down after having paused the video, we have called r of 6. Now we've called r of 2. Okay, so now entering our call of r of 2 is 2 less than or equal to 0. No, so we call r of n minus 4, which now is r of negative 2. Is negative 2 less than or equal to 0? Right? Yes, indeed. And so we called r of negative 2, and it is indeed equal to 0, so we return. So we've added it to our call stack, and now we pop it off the stack. We've taken it off. Okay, so now that's covered. We move on to r of 0, r of n minus 2, right? Is 0 less than or equal to 0? Yes, indeed. So we call r of 0, and we return. Okay, so now we've added it, and we can pop it off the stack. And once we print 2, so we can keep track of our output down here. We've printed 2. Now we've completed everything that we need to complete in order to finish executing R of 2, right? We've completed this subcall, this printing. So we have finished our execution for R of 2. So I'll pop that off the stack as well. Okay, so next up is we go back into finishing our original call of R of 6. So we call R of 4, right? A subcall. In order, always think back to what's our original goal. We want to do, rec test of 6. The computer wants to finish that method call's execution. Okay, and in order to do that, we have to complete all the subcalls involved. So we have R4 now that's been called. Okay, is 4 less than or equal to 0? No, so we continue with the rest of the body. Okay, and we call R of 0. 0 less than or equal to 0? Yes, indeed. Okay, so we can pop off the stack. Okay, and now we can call R of n minus 2, which in our case is R of 2. Okay. And actually, I'll also, to help us keep track, just everywhere we've traveled to so far, I'll have highlighted, right? Okay, but 2 is not less than or equal to 0, so we're not returning yet. We need to call R of negative 2, R of n minus 4. Okay, but negative 2 is indeed less than 0, so as soon as we push it on the stack, we are able to return and pop that off. Okay, next, we're just continuing along, right? Calling R of 0. Indeed, 0 is equal to, less than or equal to 0. So we have that done. And once we print 2, we have completed our call to R of 2 here, right? And now that that's done, we can take that off on like our call stack up. You can think of it almost as like our to-do list, right? It's off our to-do list. Got that done. And we bubble back up. So we did this. Oops, still have it in erase mode. Okay, I'll just back up so you can still have the visual. And okay, we still need oh, an R4 is now also completed, right? Because once we print 4, that's done. Okay, we're back to R of 6. What's the last thing we need to do to finish the execution of this call? Okay, print 6. This is here. And we can take that off our stack as well. And we're done. Our to-do list is cleared. Okay, and our output is 2, 2, 4, 6. Okay. So let me clear this. And as you can see here, the result is 2, 2, 4, 6. And here is another example of the same process that we went through. Yeah, and after tracing the code, you might have noticed a quick way to have gotten the final output of 2, 2, 4, 6. So notice before any call in our tree finishes executing, all the subcalls within that call must finish executing first. Okay, and also we read left to right in that subtree. So maybe let's see if I can actually undo and get that back, right? Yeah, so with that in mind, right, that this hierarchy here, the calls are being done left to right, but also all the subcalls, um, must be completed first. So I accidentally had it on erase mode again. All the subcalls, imagine it's here before I accidentally erase some portions, must be completed before the original call finishes executing. So with that in mind, would you have been able to quickly get this output just from having drawn your diagram? Okay, think about that. Okay, so now we'll clear for good. Okay, and here's another visual of the same diagram that we've had before previously. It's a bit involved, so if you find this hard to follow, that's okay. Just keep in mind, like the one we also had before. So another problem that may show up on your final exam is, given a snippet of code, what is the big O for the above code snippet? So recall that what are, the different scenarios for the different time efficiencies we may have for our algorithms, right? If we have two for loops present, for example, that are both dependent on n, it's not even for loops, but or while loops, two loops dependent on n, but not nested, that would be O of n time efficiency, right? Because n plus n is 2n, that's distinct from n squared. Okay, and if we had two nested loops dependent, both of their looping, the outer and the inner loop, dependent on n, that would be O of n squared. And so keep in mind, it's not necessarily, a big O of n squared if you have two nested loops, but in the case that both of their looping is dependent on n, well, yes. And, what if we had two nested loops and a separate loop present, right? And all of that looping being dependent on n. So, we would have our n squared plus n operations approximately without coefficients involved. And that would also just be O of n squared. Right? Because for big O notation, we disregard the coefficients and we take the leading degree polynomial term. Okay, so with that in mind, pause the video and think about what's the big O for this present code snippet. Welcome back, guys. So notice how that in our code snippet, we do have this third scenario that's written out, right? We have a for loop here that is indeed dependent on n. So we're initializing our array. And we also have nested loops, both of which are dependent on n, right? Because a dot length, the length of our array, is indeed n. As we can tell from this line here, where when we created our array, we made it of size n. And for this inner for loop, inside the while loop, is it also dependent on n? Does it make sense that we have O of n squared? And actually, yes, because the value of b is dependent on a dot length. So this inner for loop, its looping is also dependent on n, which gives us a big O of n squared. Okay. And what is the value of the variable clicker after the snippet is run for n equals 5? So you can pause the video again and work it out for yourself. Okay. And so we're updating the value of clicker in this nested for loop down here. So we can, just for now, disregard this above snippet of code. And notice how that, a dot length is, okay, so n's equal to 5. So we'll have the inner for loop for the values of b starting from 1, 2, 3, and 4. But not 5, because remember b is less than a dot length, so 5 would not be less than 5, right? 5 would be equal to 5. And what for b is equal to 1, right? So our condition is I is less than b, so we would loop through I from 0 to 1. So exclusive. So clicker would increment 1 time. For B2, we would loop for I from 0 to 2. Exclusive, okay, so twice. We would increment clicker twice. The pattern continues, right? For B equals 3, I would loop through 0 to 3 exclusive. Okay, so clicker incrementing 3 times. For B equals 4, I will loop through 0 to 4 exclusive. Okay, so also 4 times here, following the pattern. So when we add all of these increments together, right, if we add them all together, our final value for clicker, which I'll shorten to C, so 1 plus 2 plus 3 plus 4, we get our value of clicker to be 10. So the value of the variable clicker after the snippet is run for n equals 5 is 10. Clear? And if we look on the next slide, indeed, they have a similar explanation where, as we can see, because of how many times we loop, the value of clicker does indeed end to be 10. And to conclude this video series, go back and refresh merge sort with this visual at visualgo.net to help you see the sorting algorithms, in particular merge sort, which we just covered in this recitation, and to get an intuition for it, right? So as you watch the animation for the closing assignment, are you able to follow along with what's happening to the array as the animation progresses? How does the animation match the merge sort algorithm as we discussed in previous videos? And in what ways, perhaps, does the animation misrepresent merge sort as we have discussed previously? So think about that as good intuition for this. And that concludes this recitation. Good luck on your final.